Welcome to the third section about system of linear equations. One of my favorite section because that section you don't really need anything to solve these systems that we're going to present. I call this section the 6 easy examples, or I should maybe say the easier example if this is still not easy for you. But the goal though of that section is still quite noble because I will use these easier examples to teach you how to write the general solution in canonical form. So the notation in this class is a very rigorous. We want the general solution of the system of linear equation to be written in canonical form. So I'll be using these 6 examples to show you how to do that. And then for more difficult examples, we're going to use the Gauss-Jordan elimination algorithm to get there. But this is a very important section because even if in general the examples are tougher, the ultimate strategy, which is using that Gauss-Jordan elimination algorithm, is to transform a messed up system that is quite difficult into something that is easier, like these examples. So your solution will always end up looking like one of those 6 easier examples. So let's go through it. For my first example, I have a nice system of 2 linear equation with 2 unknowns, x plus 2y is equal to 5 and minus y is equal to 3. Because we're here, I'm going to also take the time to associate to these system their coefficient matrix and augmented matrix. So here you can see that the matrix A is the matrix 1, 2, 0, minus 1, and the augmented matrix, so same matrix A, 1, 2, 0, minus 1, but we have an extra column of the constant terms, 5 and 3. And this is something that we're always going to ask you first. Here's the system. Give to us the coefficient matrix and the augmented matrix. So now let's solve this system. What I like to do in these questions, I like to label my equations. So let's call the first equation, let's call it E1, and let's call the second equation E2. And as you can see here, I am looking for values for x and y that fits in this system. But the easier question, or the easier equation, sorry, is equation 2. So if I read equation 2, I can figure out what y is, because minus y is equal to 3 implies that y is equal to minus 3. So there's only one possible value for y in that possible solution, and that possible value, that value of y is minus 3. So if you give me any pair and you ask me, is this a solution? The y value of that pair needs to be 3. Now that I have 3, I can put this information in the first equation. This is also known as backward substitution. So we have x plus 2y, but now y is freshly computed to be minus 3 is equal to 5. And now if you isolate 5 here, you're going to get, sorry, if you isolate x here, you're going to get that x is 5 plus 6. So you get x is equal to 11. So we have only one value for x. Also, so what is the canonical form? What is the right way to present the solution here? Is to write this using a column matrix or a vector x, y, and then just write that pair nicely as 11 and 5, and that's my solution. A remark here that is quite important. If I ask you how many solutions do we have, so remember a solution is a pair x, y. So here the only pair that fits in this system is 11, 5. So we have a unique solution for that system. If you already know about matrices being in echelon form, you should be able to notice that matrix A is a matrix in echelon form, because if you circle the leading coefficients, they go from left to right. Same thing for the augmented matrix. Those two matrices are in echelon form, but not in row reduced echelon form, but they are in echelon form. And if you compute the rank of A, you get 2. And if you compute the rank of the other one, A augmented by B, you also get 2. and this is not a coincidence, when those two ranks are equal, you will have solution for a system. And in this case, in particular, when the two ranks is equal to the number of variables, how many variables do we have? It's x and y, so it's 2. When everything is equal, this is when you're getting a unique solution. So this is how you can use the rank of those matrices to check how many solutions do we have. So because everything is equal, the rank of A, the rank of AB, and the number of variables, boom, unique solution. In this case, using the algebra backward substitution, I was able to figure out y, then x to get my unique solution. Next example. So we have now a system of three equations, three unknowns, x plus 2y plus 3z is equal to 14, minus y plus 2z is equal to 4, and minus 3z is equal to minus 9. Again, the first thing you should be comfortable with is constructing the coefficient matrix of that system. So 1, 2, 3, 0, minus 1, 2, and 0, 0, minus 3. And then the augmented matrix, which starts with the exact same matrix A, with an extra column, okay, using 14, 4, and minus 9. And you're getting 14, 4, minus 9 for the last column of your augmented matrix. So those are your matrices. So now let's find the solution of that system. So again, here, I really like to label my equations. So let's call the first one E1, E2, E3. And here I'm going to use the exact same strategies as before. The third equation here is the easier equation because I can find the value of z. I have minus 3z is equal to minus 9. By dividing by minus 3 on both sides, you get that z is equal to 3. So there's only one possible value for z. Now I can plug this information in the second equation where I have minus y plus 2z. But now z is freshly known to be equal to 3, is equal to 4. So you can bring the 6 on the left side as minus 6. So you get minus y is equal to 4 minus 6. And then we have minus y is equal to minus 2. If you multiply by minus 1 everywhere, you get that y needs to be equal to 2. And then finally, in the first equation, we have x plus 2 times y, freshly computed to be 2, plus 3 times z that we now know is equal to 3, is equal to 14. So if you take 2 times 2 plus 3 times 3, which is 4 plus 9, that's 13. So you can bring that 13 on the left side as minus 13, and you get x is equal to 1. So this means if you assemble everything, so variable, assemble, so you bring them together, that's your canonical form. So x is 1, y is 2, z is 3. 1, 2, 3. And then here, as a remark, how many solutions, how many triplets do we have here? Be careful, a lot of people say, we have 3 solutions. No, we have 1 triplet of solution. 1, 2, 3 is my only solution. There's no other triplets that fits in that system. So remark here, again, unique solution. Also, if you look at the matrices A and A augmented by B, those two matrices, guess what? They're in echelon form. There's a reason why most of these examples are easier to solve. Their matrices, augmented and coefficient matrix, are special. They're all in echelon form except for one where we'll need to work on it a bit. So what about their rank? So if you compute the rank of A, again, here I use the word compute, but that's not a computation. So there's 3 pivots in A. How many pivot in the augmented matrix? Well, there's no pivot in the last column, so we still have 3. How many variables do we have? We have 3 variables. When all these numbers are equal, automatically we have a unique solution. Right now, it might feel like it's too much information. I'm making that remark because when you know, you know. Okay, so like it's the reason why these are easier. It's because I can use backward substitution, and the reason why I can use backward substitution It's because those matrices are in echelon form. It makes them easier to solve. My next example is almost like example one. Now my system will have only one equation. So it's still a system, but there's only one equation, x plus 2y is equal to 5. But that's it. Okay, so my coefficient matrix is just 1, 2. So 1x plus 2y. My augmented matrix is 1, 2 augmented by 5. And that's it for these matrices. Now let's solve it. So here, if I do label it, again, there's only one equation. It's a bit boring, okay, but there's only one equation here. So what's the big difference between this example and example one? In example one, we add a value for y, and we use that value inside the first equation. But now we no longer have a specific value for y. Y can actually be equal to anything. If y is 0, x is equal to 5. If y is equal to 1, x is equal to 3. So we can actually compute x. As soon as we have a value for x, for y, we can compute a value for x. So in general, how are you going to write this up? So here, unlike example one, my value for y is no longer restricted, and we call this lack of restriction freedom. So we say that y is free. So here, y is free. It can be equal to anything. The way you write this up is you say that y is equal to t, some real number. So you assign a specific value for y, and you say that this y is equal to t. And now when you put this information in the first equation, what happens is that x is going to be computed as a function of this choice. So here we have x plus 2y freshly computed to be equal to t is equal to 5. So x is equal to 5 minus 2t. So once we assign a value of y, like for example, if we say that y is equal to 0, we can compute the value for x as 5 minus 2 times 0, and you get a value for x. So in general, so canonical form, this is where canonical form will shape up to be something a bit more interesting. So the way you write your general solution, the first thing is you assemble, variable assemble. So we have 5 minus 2t for x, and we have t for y. That's called the general form of your solution. But we want the canonical form. So there's no, when it's only one solution, there's no difference between canonical or general. But for canonical form, what I want you to do is write this general solution using vectors. And the first vector are the constant, and the second vector will be the multiples of t. So the way you build this up, or the way you break this up, is you write your constant first. So for x, I have 5 minus 2t. So 5 is my constant, and my coefficient for t is minus 2. And for y, we have 0 plus 1t. And that, my friends, is the canonical form of my solution. And here, how many solutions do we have? So small remark here, not a small remark, a big remark. In my previous two examples, we had a unique solution for the first and the second example that we got from backward substitution. Here, how many solutions do we have? Well, because t can be any real number, then we have infinitely many solutions. We have infinitely many solutions. So every single t will create a different pair, and we have infinite choices. What about the ranks? So here again, if you circle your leading coefficient, both matrices are again in echelon form. We were able to find the general solution because those matrices are nice. And when we compute the rank, so rank of A is, there's only one pivot. Rank of AB, there's also only one pivot, but the number of variables in this system, so the number of variables is equal to what? Equal to 2. So the fact that the two ranks are equal means that we have some solution. But because that number is less than the rank, so that number, sorry, because the rank is less, so that, or my God, I suck, because the number variable is bigger than the rank numbers, this means that we have infinitely many solutions. So when both ranks are equal, but strictly less than the number of variables, it means that we're going to have at least one free variable, and it means that we're going to get infinitely many solution always, always. My next example is basically, again, example 2, but I'm going to remove the third equation. So now I have only 2 equations. So this example, very close to example 2. It's kind of good to look at example 1 and 3 together. Same thing for 2 and 4. So now I have x plus 2y plus 3z is equal to 14. That's going to be my equation 1. And then my second equation is minus y plus 2z is equal to 4. So I'm going to label that as equation 2. So of course, now you're probably like a bunch of pros. Okay, so coefficient matrix A, 1, 2, 3, 0, minus 1, 2, and augmented matrix A, B, 1, 2, 3, 0, minus 1, and 2, but augmented by 14 and 4. And since we're there, for those who've seen it, okay, so we have a matrix where the leading coefficients are 1 and minus 1 for both. So those two matrices are in echelon form. So one of the reasons why most of these examples in this section are easier, it's because of the nice structure of these matrices augmented in coefficient echelon form. All right, so let's solve it. So here in this example, we're no longer restricted with a specific value for z. If you remember, in example 2, z was equal to 2. Now z is free. So here, now z is free. Okay, and the way you do this mathematically, you just say that z is equal to t, where t is any real number. So just a small remark here, how come we're changing the letter here? It feels kind of weird to replace z by t. Initially, x, y, and z, we don't know. They are unknowns. But now when I write z is equal to t, I know what z is. It's anything I want. So it's no longer an unknown. It's equal to t, where t is anything. So that's the sweet distinction between saying I have an unknown for z and writing that z is equal to t, where t is anything. So now here we go. So let's compute some stuff. So in equation 2, I get minus y plus 2z. Z now known to be t, equal to 4. If you bring the t on the other side, you get that minus y is equal to 4 minus 2t. By multiplying by minus 1 on both sides, you get that y is equal to minus 4 plus 2t. So once we have a specific value for t, y is computed as a value for t. Just a small remark, we had 3 for z in the example 2. If t is equal to 3, 2 times 3 is 6 minus 4, we get back our sweet 2. So now for equation 1, so in equation 1, we have x plus y plus 2 times y, but now y is freshly known to be minus 4 plus 2t. So I'm replacing the y by its equation, plus 3z, z is still equal to t, equal to 14. And now let's find a formula for x that will depend on t. So if you distribute the 2 here, you're going to get x. So you're going to get x, hello, x minus 8 plus 4t plus 3t is equal to 14. So now I'm going to simply bring everything on the left side. So we have x is equal to 14 plus 8 minus 4t minus 3t. And when you clean everything here, 14 plus 8, that's a nice 22. And minus 4t minus 3t, that's minus 7t. Yay. So we have, again, an equation for x. So x and y are computed as a function of t. And again, here, if t is equal to 3, 22 minus 7 times 3, that's 22 minus 21, we get back the 1. So canonical form, so first general form, so variable, assemble, okay, so x, y, z. So you bring all of them together. So 22 minus 7t, that's for x. We have minus 4 plus 2t, that's for y. And then z is t as t. Okay, so, and then you break this. So that's the general form. So the canonical form, all the constants. So 22 minus 4 and 0 plus t times minus 7, 2, and 1, where t is anything. So we have, so let's do a couple of remarks here. How many solution? We have still infinitely many solutions. Why? Because t can be anything. So because we have a free variable, we automatically get infinitely many solution. What about the ranks here? So we have that the rank of A is 2. The rank of AB, just counting the number of pivots here. It's not a big fat computation in any way. So you get 2 again. But if we look at the number of variables, we get 3. And that number is bigger than the rank numbers. And that's another way to argue correctly that we have infinitely many solutions. We could test you on a test and say, hey, we have a big fat system. Let's say we have like a big fat system where the rank of A and the rank of AB is 17, but the number of variables is 19. As soon as the ranks are equal, there are some solution, but if the number of variables is bigger, it's infinitely many solutions. But if everything is equal, so if we say, hey, we have a big system, both ranks are 17 and we have 17 variables, unique solution. So you can use the rank to argue how many solutions do you have. All right, my next example is probably the only example that is not truly an easy example, in the sense that we're going to have to work this example in order to extract the solution. Example 1 and 2, backward substitution to find a unique solution. 3 and 4, as soon as we understand that they are like 1 and 2, but we have some freedom and we can just assign a free value for one of the variable and then compute accordingly the value of the other ones, you get how to get the full general solution. But this one won't be as easy. So we have a system where we have 3 unknowns, x, y, z, and 3 equations. So this is a 3x3 system. So technically, at this point in your life, you should be comfortable solving system of linear equations with 2 unknowns or 3 unknowns. And I'm going to be using this a little bit to get to some of my remarks. So the first thing here is, if we look at the coefficient matrix, that's still fairly straightforward. So 1x, 1y, 1z for the first equation, 1x, 2y, and 3z for the second, and then 1x, 3y, and 5z for the last equation. So I get my 3x3 matrix. And then for the augmented matrix, just adding an extra column for 3, 6, and 10, I have my augmented matrix. But what's interesting here is that all the leading coefficients are in the same first column. These matrices are not, both of them are not in echelon form. So this is not in echelon form. Oh no! Same thing for this one. And you'll see we'll have to work. We'll have to do stuff to that system in order to get that solution. So how do we find that solution? So again here, let's label our equation, equation 1, equation 2, equation 3. And let's try to find a solution. The trouble that we have now is that every equations have all the variables. So I cannot do that trick where, oh, I have z to compute y to compute x, or I can have anything for z to compute y to compute x. Everything is in there. So what we're going to do is we're going to eliminate some of those variables for all these equations, for some of these equations, to make it into a better structure. So what I mean by this is that I'm going to keep the x in that first equation, but I'm going to destroy the x below in the second and third equation by doing some elimination. So how do you do elimination? Well, for example, equation 3, you can take equation 3 and say that it's going to be equation 3 minus, so equation 3 minus equation 1. That will get rid of that x in that equation. And you can do the exact same thing for equation 2. You can say equation 2, I don't want an x in that equation, so I'm going to say equation 2 minus equation 1. And here, notice that I'm using equation 1 again instead of equation 3 because equation 3 is changing. So what will happen now is that I'm going to be creating a new system. So I haven't changed the first equation. So it's still x plus y plus z is equal to 3. But now I'm doing my elimination. So equation 2 minus equation 1, bye-bye, the x is gone. But now when you're doing your computation, 2y minus y, you're left with 1y. And then when you're doing 3z minus z, you're going to get 2z. And then when you're going to be computing 6 minus 3, you're going to get a nice clean 3. And now you can see that in my second equation, I only have y and z. So it's already looking better. If I continue with the same computation, so if you take x and you remove and you do subtract it by x, you're going to cancel it. But now you continue. You have 3y minus y, so you're getting 2y now. And then you have 5z minus z, which gives you 4z. And then finally, you have 10 minus 3, which gives you a nice clean 7. All right. For our system to be ready for backward substitution, what we need to do is get rid of that y in the third equation. So again, if we label our equations, so first equation, second equation, and third equation. So I want to get rid of y. So what I'll do is I'll take equation 3, and this equation 3 will become equation 3, where I will remove 2 times equation 2. And I need to use equation 2. If not, if I use equation 1, I will reintroduce an x in my third equation. And remember, you don't want to reintroduce an x in your life. This is almost like advice for real life. Anyway, so when I do this final operation, what happens? So I'm not touching my first equation, so I can rewrite it quickly, but carefully. I'm not changing my second equation, so I can also rewrite it quickly, but carefully. Now, when I do my elimination, so if you take 2 times y, sorry, 2y minus 2 times y, you're going to get 0y. So, and also when you're going to take 4z minus 2 times 2z, this is also going to give you 0. So I'm going to write this up like here on the left side. We destroyed everything, not just the y. And then on the right side, what do we have? We have 7 minus 2 times 3, which will be 1. Uh-oh. So which will be 1. Uh-oh. So 0 is equal to 1. I don't think so. So what happens here when you do these eliminations and you get that 0 is equal to a number, that's impossible. In other words, there's no triplets that will fit in that equation. So automatically you can answer that there's no solution. And actually this is the first time that we get no solution. And this is actually the last possibility. When you solve this system, you get either a unique solution, like in our example 1 and 2, infinitely many solution, like our example 3 and 4, where we had a free variable. And sometimes we get no solution when you do these elimination and you get these bad equation of the form 0 is equal to a non-zero number. That's just not possible. So small remark here, also, we had to work to see that there was no solution here. We had to do these eliminations to make sure that there's no x in the second and the third equation and no y in the third equation. One reason why we had to work is because our matrices were not in echelon form. But now we got this conclusion, no solution. So if you actually look at this new system, so if you look at this brand new system, and you are going to extract from that system the new coefficient matrix, let's call it A star. So the new coefficient matrix would be 1, 1, 1, 0, 1, 2, 0, 0, 0. And that matrix is in echelon form. And the rank of that matrix is actually equal to 2. We have to pivot. And meanwhile, if you look at this A star augmented by, let's call it B star, so if you look at that new matrix now, after doing some work to it, we get 1, 1, 1, 0, 1, 2, and 0, 0, 0, augmented by 3, 3, 1. And what's interesting now is that the rank of that matrix is actually equal to 3. And actually, when those ranks are not the same, so that rank is not the same as the rank of A because we have this extra pivot in the last column, then that's one way to see that this system has no solution. As soon as the rank are not equal, and the only way the rank of A is not equal to the rank of AB is if you have an extra pivot in the last column in the augmented part. This means that there's no solution because you're going to get an equation of the form 0 is equal to something. So when the ranks are not equal, there's no solution. But we could not see this from the beginning. We had to work for it. But it's not too bad. 3 elimination, and we were able to extract the general solution, which in this case was completely empty. All right, last example. So we have now a system of 2 equations with 4 unknowns, wx, y, and z. So here we can extract the coefficient matrix, 1w plus 1x plus 2y plus 3z. And there's no w, no x, minus 1y, and 2z. That's my coefficient matrix. And here you can see that this matrix, if you circle the leading coefficients, you're going to get a rank of 2. So this is in echelon form. And the rank of that matrix is 2. And meanwhile, for the augmented matrix, so same A at the beginning, just one extra column for the constant terms. So 2 for the first equation and minus 1. Again, for that matrix, if you circle the leading terms, you can see that this matrix is also in echelon form, and the rank of that matrix is also, if you count the pivots, equal to 2. So both ranks are equal. So here we know there's some solutions, but because the rank of A is equal to the rank of AB, but this rank is equal to 2, which is less than the number of variables. How many variables do we have here? 4. We know there's going to be infinitely many. So infinitely many solutions. So even if we're not computing anything, we already know how many solutions we're going to get just by looking at the ranks. So let's build this general solution. So for that question, I'm going to start with equation 2 because it's the easier equation. What we see in equation 2, Equation 2 looks like our third example where we have two variables, only one equation, but I can simply say, well, if I assign a value to z, I'm going to be able to compute the value for y. So here we go. So let's say that z is free. So this means that we can assign to z a parameter. So remember, when we call one variable free, this is no longer an unknown. We know its value. It's anything we want. Now, in that same equation, now we can construct a formula for y. So we have y minus y plus 2z, freshly computed to be t, is equal to minus 1. So y minus y is minus 1 minus 2t. Or if you multiply by minus 1, you get 1 plus 2t. That's my equation for y. So if I know z, I can compute y, no problem. But now if I go to equation 1, what happens? I know what z is. It's t. I have a formula for y. It's 1 plus 2t, but I'm still stuck with two variables. But the idea is just to repeat the same process. If I just assign a value for y now, a new variable, so if I make this variable free, then I can compute w. So here, I'm going to say that x is also free. Of course, free in its own right, so it's not going to be equal to t. It's going to be equal to some other number. So I'm going to use s, and that's very standard. So let's say x is equal to s, a real number. And now what we do is we compute w. So we have w plus x, freshly computed to be s, plus 2y, freshly computed to be 1 plus 2t, plus 3z, which is 3t now, is equal to 2. Now, if I isolate w, so you get that w is equal to, I'll just multiply the 2 at the same time and shift everything on the right side. So you get 2 minus s minus 2 minus 4t minus 3t. So w is equal, the 2 will cancel each other. You're just left with minus s minus 7t. And that's my formula for w. And now you can just assemble everything. So here we go. Variable, assemble. So w, x, y, z is equal to, so w freshly computed to be minus s minus 7t, x, which is simply s, y, which is 1 plus 2t, and then z is simply t. You can see I'm kind of misaligning my stuff here because I want to write things in canonical form. So in canonical form, I start with the constants plus multiple of s plus multiple of t's. The order does not really matter here. The point is to break this into pieces. So for constant, there's 0, 0, 1, 0. Multiple of s's. In the first equation, I have minus 1. Then I have 1s, no s, no s. And for t, I have minus 7 in the first one. I have none for x. I have 2 for y. And I have 1 for z. So where st is inside, not inside, but any real number. So, and the final remark, but we already knew this, okay, from my rank analysis, that we have infinitely many solution for that system of linear equation. So one last little remark before I go to the next section. I chose Z to be free and X to be free. You could have chosen Y or W instead, but the reason why I chose X and Z, it's because we will see in the last section that when you have a matrix in echelon form, that the free variables can also be understood and better understood using the Gauss-Jordan algorithm as the column that are pivot free in your coefficient matrix or augmented matrix. What I mean by this is that the first column here is W, the second is for X, the third one is for Y, and the last one is for for Z. I have to write it down because my menu is in the thing here. And you see that there's two columns without pivot that are pivot free. So the column for X is pivot free. So the column for X is pivot free, and also the column for Z. And those columns that are pivot free, if you are using the Gauss-Jordan algorithm, those are the ones that you have to select to be the free ones. But anyways, this question, even if it's slightly more complex because there's two free variables, we were able to extract the general solution because, again, those matrices right from the beginning, A and A augmented by B, were in echelon form. When things are in echelon form, everything is just beautiful. All right. So for that section, for the 6 easier examples that will set up, like the last steps for questions in general,